Let's get started. So today I'm going to cover a simulation, which you have been doing for a while. Arguably, this lecture could have come earlier as well, but maybe you will appreciate it more now that you've dealt with simulation a little bit in this class. I mean, simulation is by no means unique to computer architecture. It certainly has unique aspects to computer architecture, but it's done in many, many fields. And it's very important, especially in fields where you want to predict the future or create the future, which is certainly architecture. But some other fields also employ it, and we may briefly discuss it in this lecture too. But we're going to focus a lot on architecture, architectural simulation, and especially focus on memory, which you're going to do a lot more in the remaining labs. Okay, so let's jump into it. So basically, we're going to talk about simulating systems, and some focus will be on memory later on in the lecture. I also think about this as how do we evaluate new ideas for new architectures in general, or new systems in general. You have this idea, great idea, it's seemingly great idea. How do you put some evaluation into it, and how do you actually, how can you actually trust the accuracy of your evaluation? Because clearly your idea has not been realized yet in a real setting, right? So that's the basic question that we're going to answer. We're going to focus a lot on simulation, but simulation is definitely not the only way to answer that question. Basically, the question is, how do we assess how an idea will affect the target metric X? Your target metrics could be anything that we discussed in the first lecture. It could be performance, clearly. It could be energy, it could be security, it could be reliability, any of the metrics that are used to measure any of those different things, clearly, because even performance can be measured in multiple different ways, right? As we know, clearly in the end, execution time is the best way for a given application. But if you're running many applications, there's system throughput, there's fairness, there are many, many different metrics that you want to optimize. And as you already also know that it's not just about a single metric, it's about multiple metrics at the same time. The priority of those metrics may be different. Basically, it's not. It's a complicated problem because you have an idea that doesn't exist yet. How do you evaluate it? And there are a variety of evaluation methods available for this, and different fields, let's say, or different areas in different parts of science use different methods. And in computer architecture, you can also use many of those methods that are available to people. One is theoretical proof, for example. Can you theoretically prove that your idea will improve performance by more than 10%, let's say? Usually this is not easy to do, especially with performance. Potentially you can prove security guarantees about your system, but even that is not easy, as we've discussed in earlier lectures. But theoretical proof is nice if you can do it, but usually it's very, very difficult to do it in computer architecture because you're very much dependent on the workload that's executing. And as we discussed also, we don't even know what kind of workloads are going to be executing for a system that you're designing today, because that system may be used 5 years down the road, right? So you may not even know what workloads you're going to execute. How are you going to provide proofs for it? Now you could do a worst case proof, but worst case is actually very, very conservative. If you want to evaluate your idea with a worst case proof, then your idea may not have a lot of room to improve things, because worst cases, as we discussed many times, is not a great optimization point. You really want to optimize for the common case in computer architecture while not doing badly in the worst case. But if you really want to, if you really optimize for the worst case, then your common case performance may be terrible, for example. And that's not a good optimization point, as we discussed. Okay, so theoretical proof is very, very interesting, but usually, very often actually not applicable to computer architecture. There are exceptions, of course. Analytical modeling and estimation is something that's actually potentially applicable and is done in many systems. This is basically, you basically gather some input parameters to your system and estimate how much, what would the performance be using those parameters. So you have this bright idea of enlarging your cache by 10x, for example, let's say. and you want to estimate how much performance improvement enlarging the cache by 10x would provide you. You build an analytical model, which could be a spreadsheet, let's say, and this analytical model may have some inputs in the system, right? What are the other parameters of your processor, let's say, iCache, Dcache, pipeline depth, branch predictor accuracy, etc. These are not simulated in any way, but this all of it, everything becomes an equation, let's say, and you essentially evaluate the effect of the change you're planning to make on the result, or on the evaluation of the equation. You can think of an analytical model as an equation that expresses the output metric X in terms of some parameters of the system. And clearly, this can be very, very complex. This can be very, very simple, right? For example, sometimes people have used instructions executed as a good estimator for energy consumed, relative energy, of course, not absolute energy. So basically, if you want to estimate how much energy you're going to consume, dynamic energy you're going to consume, just check what will be the instructions, what is the number of instructions that you're going to execute will be. And you can get this information with some, in some way, of course. You need to get the parameters of the model in some way, in that case. How do you get the number of instructions? Well, you can imagine different ways of doing that, profiling your program, for example. So an analytical model needs to be driven by a mechanism where you get the parameters and estimate the parameters into the equation, basically. So this is clearly very fast, potentially, if you do it nicely. And it, of course, it could be very accurate, potentially also. But usually it's not as accurate as what we're going to describe, which is simulation, because you're really ignoring potentially a lot of effects. And in the end, you're really trying to fit an equation to describe a system. And it's not, if your system is complex, I mean, you could, of course, fit many, many equations to describe the system and make things more complex. But this turns out to be not so easy to do, especially when you go into a very complex system. You can, to a first order, you can estimate some things. Maybe you can estimate how much performance benefit you will get from a 10x cache. But it may not be very easy to do other type of estimations relatively easily. But even the 10x cache may not be easy. You still need to, you may still need to derive your analytical model with some profiling data that you get from your application, because in the end, as I said, you're very much application dependent. Your analytical model needs to describe the system really well, but also it needs to describe the application that's executing really well. How do you, for example, analytical model unfairness in a system? So if you once you, and also target metrics, metric is very important, basically. Some metrics are easier to model, performance. Some metrics are harder potentially, like unfairness or predictability of the performance, or potentially reliability. I'm not sure. It depends on what you assume. But basically, this is a good tool for an architect, but it's usually not very accurate, and it requires a lot of experience to get the analytical model right. That said, usually what happens whenever you design a real system is you use analytical models to do some estimation as to what your initial parameter space in your system could be. Of course, here analytical modeling is nicer if you could actually incorporate some machine learning into it as well. So potentially you can learn the parameters of your model that you want to construct. But to be able to do that, of course, you may need to do some simulation that we're going to discuss next. Okay, so simulation is nice because what you can do with simulation is you can take a workload and take an imagined system, write it up in software, and simulate what kind of performance, energy, reliability, etc. you would get based on the simulation of the complete workload, for example. So this here, actually, the opportunities are endless, let's say, because you could go into a lot of detail into your simulation, or you could decide to be more abstract in your simulation. For example, you can decide that I don't care about the accuracy of my simulation as much. I just want to get the big things right in my design. So you can be very abstract in this case, and maybe you basically have some simulation error you always have simulation error actually, but you increase your simulation error intelligently and also intentionally, such that you get the bigger parameters right. So this is actually we're going to talk about this in more detail. So basically you can do this at varying degrees of abstraction and accuracy. If you're too abstract, then you get closer to an analytical model potentially. If you're less abstract, you get closer to a real prototype or a system. Okay, but this is another tool that's available to you as an architect to evaluate your potential idea. The other tool, of course, is prototyping with a real system. So existing systems exist, like FPGAs, reconfigurable architectures, potentially somewhat configurable existing systems. If your idea is not modifying things drastically, you can potentially evaluate your idea by having an implementation as a prototype in a real system. Maybe it's not going to be exactly the same way you're going to really implement when your idea is full-blown implemented. But an FPGA, for example, a reconfigurable architecture provides you a way of getting an estimate in terms of the performance. You're still limited to the FPGA's clock frequency, for example, maximum clock frequency. If you're prototyping, for example, a general purpose CPU on an FPGA, you would be limited by the clock frequency and the connections that you have and the space that you have on the FPGA. So you may not get a fully accurate picture of what kind of performance you would get when you actually implement your idea in the real system. But you may get closer potentially, and you may actually have to solve some problems that you may not otherwise have to solve in simulation, and certainly not in analytical modeling, because you're actually really implementing your idea in a prototype system. But keep in mind that this real system is always different. The prototyping, what's the difference between prototyping and implementing your idea? Prototyping is always done on a system that's different from a system where your idea will be implemented. So that's the difference between this bullet over here and this next bullet. Next bullet is a real implementation, of course, right? So a real implementation says, you want to assess your idea? Well, go and implement it as it will be implemented in a real system. So pay all of the costs to do that, and then you'll get a really, really accurate number, hopefully. At least for the initial version of your real implementation, right? Maybe not for the nth incarnation of your real implementation. Because, for example, the first vector instructions that were implemented by Intel were clearly analytically modeled first, and then simulated, and then prototyped, and then really implemented, for example. That's how it usually goes in architecture. You usually try to get an estimate of what kind of performance benefit you would get with analytical modeling, and then you simulate it, and then you try to prototype it as much as possible, and then you really implement it. But that first version, after real implementation, may change based on the feedback you get from the software, for example, and then you may decide to change the implementation again. Okay, but this is clearly another method that's available to you. For example, if you want to increase your cache size by 10x, you say, well, tough luck. I'm going to implement that 10x cache, and I'm going to really get the results. Okay, and then I'm going to decide whether I'm going to increase my cache size by 10x. Now that sounds a bit stupid, right? Clearly, because I just basically did all of the implementation to decide whether or not I'm going to implement it. So that's exactly why you don't do the real implementation in architecture before you make a decision, because real implementation is extremely costly. And if you actually do the real implementation, then you've actually implemented. What are you going to see after that, right? If you see that your idea is terrible, well, again, you wasted a lot of your time doing a real implementation. So basically the idea of these three parts, let's say, not the theoretical proof, but not the real implementation, but analytical modeling, simulation, and prototyping, is to cut the time it takes to make a decision, such that you make a good decision without actually going through a huge amount of effort. And clearly, you can analytical model can be much faster but less accurate. Simulation can be done at varying degrees of abstraction and accuracy and speed, as we will discuss. Prototyping is usually slower because you're still implementing things in a real system, except it's not the system that you're going to implement your idea in. So it's easier than a real implementation, but it's still quite expensive in terms of time and resources that you dedicate to it. But you may potentially get an accurate number. Again, be careful. This list going from theoretical proof to real implementation isn't ordered by accuracy or speed actually. Usually you get more, you can implement your idea and test it faster if you prototype it, slower if you prototype it compared to simulation, but that's not always true. Some simulators are so hard to modify, so difficult to modify that your idea may take much longer to implement in simulation compared to a prototype that may be easier to modify. So keep that in mind. And also, your prototype may not be very accurate because it's not the same system your idea is going to be implemented in, right? Keep that in mind. Your simulation actually might be much more accurate than your prototype. Similarly, your analytical model, if you've done things well, and if you actually used very good experience, if you model things well, can be more accurate than simulation and prototyping. Clearly, it's not going to be more accurate than your real implementation, because the real implementation, if you don't have bugs or anything in your real implementation, that's what you're desiring for. So that's why I think being an architect is also an art, because you have these evaluation methods that are available to you, and you need to choose between which evaluation method you use to evaluate your idea. And there's no clear cut. For example, the other thing to keep in mind, I think, is what does it take for you to do to convince yourself or someone else to take your idea in? Prototyping with a real system may not always be the best case, actually, because let's say you have this greatest idea of a new execution model. You prototype with an FPGA, but FPGA is bottlenecked by some particular, let's say, processing in memory. Let's say I'm just using it. Processing in memory is your great idea. You implement it on an FPGA, but FPGA is fundamentally bottlenecked by memory, right? And as a result, you may not actually be getting good, accurate numbers on an FPGA compared to simulation, where you're not bottlenecked by memory bandwidth. Or you can actually write your simulator such that you eliminate some of those bottlenecks and more accurately model what kind of memory bandwidth, what kind of memory latency, what kind of memory energy you would be getting if your processing units were actually inside the main memory itself, as opposed to the real system, which clearly does not have it. So this is a case in point, I think, to consider. In simulation, you have a lot more flexibility. Whatever you can imagine, you can simulate at some abstraction level. And that can actually make you a lot more accurate than prototyping with a real system. And that's true for analytical modeling also. But you need to consider what kind of idea you're examining to decide what kind of evaluation method you're going to use. So usually these three are the major evaluation methods that we use in computer architecture. Theoretical proof is usually not available to us, and real implementation is usually very costly, and you would be defeating the purpose of your evaluation method if you're actually doing a real implementation of everything, every idea that you have. And this is, you can imagine that this is impossible to do, right? Because clearly when you design architecture, let's say from scratch, you have hundreds, if not thousands of design decisions you need to make. How are you going to make those design decisions? Are you going to actually do a real implementation of all combinations of those thousands of design decisions? Again, it doesn't sound smart, let's say. It's not feasible, actually, I would say. Less than smart. Okay, so we're going to talk a lot about simulation here, but let me tell you a little bit more about the difficulty in architectural evaluation a little bit more. So apart from everything I said, the answer is also usually workload dependent. For example, think caching. You cannot say caching is always useful, right? For random access workloads, caching is useless. For streaming workloads, caching is of limited use because your caches will be overloaded. For some other workloads whose working sites, for example, fits in the cache and they have good locality, they're not that random access, then caching may be useful. So you're very much workload dependent, even in a very simple idea and a widely deployed idea like caching. Right? Pipelining is similar. How effective your pipeline is dependent on what kind of dependencies you have in your system. Clearly, out-of-order execution is an extension of pipelining. That's very much workload dependent as well. And any idea we talked about is also potentially workload dependent, right? Memory scheduling, clearly we discuss this a lot in memory scheduling. But even Radar, for example, what kind of performance benefits you're going to get out of Radar is very much dependent on how memory intensive your workload is, for example. Even though Radar is less workload dependent compared to many ideas we've discussed, because Radar tries to exploit the underlying technology parameters, but the benefit you would get in terms of performance and energy is very much dependent on the memory intensity of the workload, as we also discussed. Okay, and okay, as if this is not enough, workloads change. Workloads are not static. At this point, you may be designing a hardware architecture for going into the market 3 years later, maybe 5 years later, I don't know, but it's going to stay in the market maybe 10 years, right? So your architecture needs to adapt to those workloads. So Apple, for example, released their recent architecture. I'm sure it was designed for a number of years before it was released. Now, whether or not it's going to do well is dependent on how well they potentially predicted what the workloads would do, right? Okay, so workloads change, and you need to somehow take that into account when you're doing simulations, right? For example, does it really make sense to simulate the workloads of today for a system that's going to execute workloads 10 years down the road? It's not clear, right? And how do you actually guess what are the workloads that are going to be executed 10 years down the road? If you're fundamental enough, maybe you figure out what are the key workloads that don't necessarily change, or what are the things inside these workloads that are so fundamental that things are not going to change as much, and you simulate those, and maybe you actually look at those things. But it's always good to have a bigger picture of the end-to-end performance of a workload, not just small kernels that are part of it. Also, a system has many design choices and parameters. I've discussed this earlier. I said you have hundreds, or if not thousands, of design choices you need to make. Architect needs to decide many ideas and many parameters for a design, and not easy to evaluate all possible combinations. In fact, not possible to evaluate all possible combinations if you're designing a big system. And system parameters may also change. I mean, system parameters are not necessarily constant as well. They can be configured in a real implementation, right? For example, clock frequency is not constant today. Voltage is not constant today. Even number of cores may not be constant today, depending on how you design things. Cache space may not be constant, because you can actually allocate it depending on the partitioning that you do dynamically. So today, actually, things are much more dynamic as well. That makes it a little bit difficult, even more difficult in architectural evaluation. So that's why simulation is actually very useful, because you can evaluate many potential options much more quickly if you have designed your simulator well, and also accurately, again, if you designed your simulator well. And you can also modify your simulator relatively quickly to add more options to it, if you design your simulator well. So of course, this goes back to how you design your simulator well, and that goes back to a lot of experience in designing simulation. And that's one of the reasons why computer architecture is a lot of art. And this is also one of the reasons why some of the best computer architects are actually really great software engineers as well, because you need to know a lot about software engineering to design a very, very good simulation infrastructure. And I've seen many simulator infrastructures employed in industry as well as academia, and the best ones are actually the products of really good architects who are also very good software engineers. Okay, so let me go into simulation. I call this the field of dreams, because you can dream about anything as an architect. The question is, how do you evaluate the goodness of your dreams, right? But basically, at some point, you need to assign some reality value to your dreams. And as we said, an architect is in part a dreamer, a creator. And simulation is a key tool of the architect to allow the evaluation and understanding of non-existent systems. Because in the end, you're really designing a non-existent system. So simulation enables many things. That's why it's very powerful. It basically enables you to explore many dreams, many potential ideas. It enables you to compare those potential ideas. Do I want to design an in-order processor versus an out-of-order processor, for example? Well, simulate and see, right? Do I want to design a 1 megabyte cache, 4 megabyte cache, 8 megabyte cache, 16 megabyte cache, 32 megabyte cache? Well, let's simulate and see what makes sense, right? So you can actually do a lot of simulations to really explore the design space. And again, as I said, you can even automate some of that simulation, assuming you're not creating new ideas, of course. Especially the design space exploration can be automated using a lot of machine learning models that can explore things, potentially, for example, using genetic algorithms, right? So there's a lot of interaction, I think, in simulation, in architecture and machine learning, as well as we have also been discussing in the past few lectures in terms of design. But it's also this machine learning architecture interaction also happens in design space exploration. Okay, but simulation enables you to have a reality check of your dreams, because hopefully, if you design your simulator nice, the simulator will tell you reasonably accurately how good your idea is, right? It enables you to decide which stream is better, as I mentioned. Okay, so these are the good parts of simulation. So clearly it enables you to achieve something that you cannot otherwise achieve without going through full implementation or full prototyping, and without going through the pitfalls of analytical modeling, let's say. So it has a special place in an architect's toolbox. But there's a downside of simulation, like with any other evaluation technique, I will say. But potentially this downside is worse with simulation and analytical modeling. It basically enables you to have the ability to fool yourself with false streams. Now, what does this mean? Basically, if your simulator is not good, and if you're not careful about what you're doing, you may actually get a number that's useless. Useless meaning that it's not accurate. But the problem is that you don't even know that it's not accurate, right? Because you don't have a bound on the error check, because simulation is somewhat of an open loop thing, especially if you're simulating characteristics like performance and energy, and let's say fairness that you cannot easily verify without having the real system. You can of course put in checks to see if you're doing something wrong along the way, and a good architect always puts in a lot of checks to see if there's something problematic in the simulation, and so that they can catch it. But in the end, you don't have the ground truth. Well, you don't have the ground truth in terms of performance because you don't have the real implementation, right? And that's always going to be the case. Whenever you're predicting something in the future, unless you go and implement it, you're not going to have the ground truth. That's why it's an open loop kind of exercise. So that's why you can fool yourself easily if you're not doing things right. And this is where, again, art comes in, because science, for example, clearly relies on having the ground truth. I mean, of course, it helps with exploration of things, but if you don't have the ground truth, you cannot really compare to that ground truth. And as a result, there's a very real danger of getting wrong predictions or estimations of how good your idea is. As I said, this is not specific to architecture. Any field that has a simulation, for example, drug simulations, right? They also have the same problem. Weather simulations, clearly, they're not accurate many of the time as expected, especially in places like Zürich. In fine grain, they're not very accurate because they also do a lot of what we're going to describe, a lot of trade-offs that we're going to describe in simulation. So clearly, accuracy is an issue whenever you do simulations in terms of the future. But you got to be very careful in terms of understanding how badly you're fooling yourself. So one good thing about simulation is sometimes you do simulation. So we'll talk about different reasons why you do simulation also. But sometimes you do simulation to get a sense of what is the big picture? Meaning, should I do in order execution or out of order execution? In that case, as long as a simulator is relatively accurate, relatively meaning as long as it's accurate in its single bit, meaning whether out of order execution is better or in order execution is better, and maybe some confidence level also, then you may be okay, right? But again, life is usually not that black and white as an architect. You want to know how much is out of order execution better compared to in order execution, right? Then you need to go and decide. So if your simulator error is less than the tolerable error that you have, then that's good. But how do you know the simulation error is always problematic in architecture? Again, as I said, this is not specific to architecture. Other fields also have this problem. And this problem becomes worse with analytical modeling. It potentially is better with prototyping, but not necessarily better with real prototyping, because real prototyping on a real system, as I said, is not the same thing as implementing on the same system that you are imagining your idea would be implemented in. Okay, so keep these in mind. These are caveats. And while you're doing simulation in this course, you're doing a lot of simulation, that's especially high-level simulation. We're going to talk about high-level simulation also, because it's faster. That's why we do high-level simulation. You're enabling a lot of good things, but you're always in the danger of fooling yourself. Okay, so let's talk about high-level simulation. In this course, you're doing high-level simulation. We decided you don't do Verilog level or RTL, register transfer level simulation, for example, which was done in digital circuits, digital design and computer architecture. That's the new name of the course. That's the freshman course. And although also in the older incarnation of the course, we had some RTL level simulation that were done. We may reintroduce them in future incarnations, but you're lucky or unlucky, depending on your perspective, that we don't have RTL simulations in this particular instance of the course. All of the simulations, the simulation labs you're doing are actually high level. So what does this mean, basically? This means that you're operating at an abstraction level that's much higher than gates and wires, for example. If you're doing RTL, register transfer level, you're very close to real hardware. Essentially, you're really putting in the gates and wires and you're connecting them in some way. The problem is, if you do this for every single idea, this is intractable, especially for design space exploration, because you have it becomes too time consuming to design and evaluate, especially over a large number of workloads, especially if you want to predict the performance of a good chunk of a workload on a particular design, and especially if you want to consider many design choices. And let's assume that you just deal with the cache. You're not dealing with the cache, of course. The system has many, many components, but let's pick the cache. Cache has many design choices, right? The size of it, the associativity of it, the block size of it, the insertion algorithm you employ, the eviction algorithm you employ, the promotion algorithm you employ, the partitioning algorithm you employ, et cetera, basically. There, you can add more to what you put into your cache, clearly. How do you coordinate with the DRAM controller? So you can actually, the sky is the limit, even in a contained structure like the cache, right? And if you want to have an RTL implementation of the cache, plus an RTL implementation of your processor, and look at all of these design choices, try to explore all of these design choices in a real workload that you want to execute for a long enough time, let's say 10 seconds of real execution time. So 10 seconds of real execution time on a real system actually takes much longer in an RTL level simulation, because an RTL level simulation is really simulating what's happening at every single gate that you have in the system. So you won't get much far. In fact, you can do some calculations if you're really interested. RTL level simulation is usually much slower than executing, let's say 1 kilo instructions per second. I'm actually much slower, orders of magnitude slower than 1 kilo instructions per second. So if you want to simulate 10 seconds of execution, you can imagine it's not going to work out well, right? So basically, this is too detailed. I will say intractable for making design choices, if you want to consider all of these things that we discussed. If you want to consider only 100 instructions executed in some workload, maybe 3 or 4 workloads, or let's say even 100 workloads, then this may be okay. But that's not what we are usually setting out to do as architects. We usually want to simulate an entire workload, let's say. Let's say a database query that goes to a huge database. What's going to be the latency of this database query if I have my great idea of a new caching algorithm for eviction and promotion? Okay, I've even constrained for you the design choices over here. I set everything else, but I'm just looking at the algorithm. Now that's intractable again in terms of time it takes to execute, let's say, tens of seconds or hundreds of seconds, whatever it is that it takes to execute that query, right? Okay, so hopefully this is convincing. It'll be even more convincing if you actually done RTL simulation. I'm hoping most of you have done RTL simulation at some point in your lives. You didn't do it in the first labs because we've eliminated that, but in the future that can come back, because knowing RTL simulation is also important. So, okay, as I said, cache is not the only block. If you want to look at memory control and scheduling algorithms, this becomes even more sophisticated because now you need to have the RTL for all of the parts of your system. In order versus out of order execution, now you need to have the RTL for both of those. Reservation station sizes for out of order execution, load store queue sizes, register file size, etc. Now you have the RTL for everything very cleanly. And imagine what else. If you omit the RTL for some of these things, you can potentially have higher level simulation that is coupled with your RTL. Now that's nice potentially, but why are you doing RTL for only these things becomes a question then, especially if you're trying to evaluate performance at a high level. So RTL is usually not a good abstraction level to get a good idea of the design space exploration and a high level impact of your idea on a metric X. So if your goal is this, explore the design choices quickly to see their impact on the workloads we're designing the platform for, then RTL is not a good choice. You need to go higher level. You need to become more abstract, like what we have been doing in the course. But again, depending on how you implement things, you can be more abstract than actually. You can be more abstract or less abstract. Okay, before we go into more abstract, let's talk about different goals of simulation, because this also determines what kind of simulation you do. So if your goal is to explore the design space quickly and see what you want to potentially implement in the next generation platform, or propose as the next big idea to advance the state of the art, as we often do in research, for example, the goal is mainly to see the relative effects of design decisions. If you're inaccurate by, let's say, 3%, maybe it's not a big deal, right? Unless that 3% is what makes the difference between one idea and the other idea, right? Of course, you always have the threshold of error and the actual error, and you need to decide which idea is better. And if your signal is less than the noise, meaning error, then you have a problem. Right? But if your signal is much higher than the noise, if you have a big idea, let's say processing in memory, and the performance improvement that you get is 100x, and your error is around 3%, somehow estimated, then you don't care about that 3% probably, because your goal is not to be extremely accurate. Right? And that's usually the case in these under these circumstances, basically. For example, let's say I'm Intel and I want to implement the next generation platform 5 years later, and I'm designing everything from scratch, and I want to explore the design space quickly to figure out what are the things that I want to put in. Do I put in processing in memory? Do I put in the best memory scheduling algorithm? Do I put in the best caching algorithm? Do I put in heavy out of order execution, a huge instruction window, for example? All of these questions, well, you don't want to do that with very low level simulation. And that's true for research also usually. But that's not always true, basically, because it depends on the goal. If your goal is exploring design space quickly, you cannot afford to actually do things at a very low abstraction level. Okay, an opposite goal, which I believe is really at the extreme of this, is to match the behavior of an existing system exactly, so that you can debug and verify it at cycle level accuracy. Or so that you can propose small tweaks to the design, not large things, very small tweaks that can make a difference in performance or energy. Or you can fix the bugs, right? Let's say some timing bugs, performance bugs, etc. So if your goal is this, then the goal is very high accuracy, clearly. Then you really want to be as detailed as possible without actually, of course, burdening yourself, so that you can represent the exact behavior of the existing system as accurately as possible, so that you can actually do these things that I just discussed, debug things or propose small tweaks. So here we're at the exact opposite end of the spectrum. And there are people who do this actually. For example, in major companies, some of the most meticulous people are dedicated to doing this actually. They like doing it, they enjoy doing it. But this is also called, let's say, simulator verification and validation. They basically design the simulator or tweak an existing simulator so that they can match the behavior of that simulator to the actual implemented system as much as possible. The simulator could be written in any language. It could be C level, it could be RTL, doesn't matter. You're trying to match the behavior of an existing system as much as possible with high accuracy. And these people calibrate that simulator. And usually they try to aim for errors that are less than 2%, 3% or so. And again, that error may be unacceptable under some cases, right? So it's good to keep that in mind. Even RTL is simulation. So whenever you design RTL, this is not the real hardware. Keep that in mind. Actual implementation is very different from not very different, different from RTL. RTL is a representation of what's going to be implemented. What actually gets implemented may be different from RTL because the tool underneath did some transformation into the layout, let's say, in a different way than what RTL designer actually envisioned it would be implemented. Right? As a result, you may actually get a different timing in the end. If someone is designing, taking an RTL and translating to a custom layout in a real system, then again, there might be a difference between what the designer interprets and what the RTL designer or RTL coder decided to put in, right? So there may be differences in interpretation and implementation. So even the RTL doesn't exactly match the behavior of real systems as much. I've seen many examples of this in real companies, for example, and usually RTL has an error bound of somewhere between 1 to 3% compared to real hardware that is supposed to implement that RTL. So what do people do? After they get the hardware, they go back to the RTL and they try to match the behavior of the existing hardware to the RTL simulation. And they actually improve the RTL at the same time that way. And they also figure out why did the real hardware didn't match the RTL. And usually the answer is someone who's custom designing the logic took some shortcuts to minimize area, whatever reason they had, that made the behavior of the actual hardware implementation different from the RTL itself. Okay, it's very interesting, clearly. And if you actually close the loop such that you make the RTL better, as accurate as possible, then you're getting closer to the real hardware. But keep in mind that even RTL has a margin of error compared to real hardware. Okay, I've given you both ends of the spectrum, I believe. In research and thinking big ideas, you want to explore the design space quickly. In matching the behavior of an existing system, you want to be as accurate as possible. But there are other goals in between. You may want to refine the explored design space without going into a full detailed cycle accurate design. Basically, this is the next level. After exploring the design space quickly, you decided on some things. Now let's go into the next level. I've decided I'm going to do out of order execution. How am I going to implement this out of order execution? So maybe you want to go into more detailed design, more detailed simulation, but not as less detailed as what you would do with an exploration of the design space. And also, you may want to gain confidence in your design decisions made by higher level design space exploration. Then you may actually want to go into a little bit lower layers. Okay, you say, oh, okay, I have this design space exploration. It looks good, but let me try to verify it by going one more level down and implementing things a little bit more detailed. Maybe you don't go all the way down to matching the behavior of a potentially existing system, but you do a little bit more due diligence to actually be more accurate. So clearly, many other goals are in between, and you need to know what you're doing and what your goal is to actually design the right simulator at the right level of abstraction to get you to the correct decisions in the end. Okay, so hopefully that's clear. Now that said, all simulators have trade-offs in the end. And again, this is going to be very general. This is not just about computer architecture, but computer architecture is a place where we feel this a lot clearly, because simulation takes a lot of time in the end. I mean, real implementation clearly takes a lot more time, but simulation takes a lot of time to decide what to really implement in the end. And there are three metrics to evaluate a simulator. One is speed, the other is flexibility of the simulator, and the other is the accuracy of the simulator. And usually you cannot get it all. This is one of those things where you get at most 2 out of 3. And if you want to get 3 out of 3, you need to be extremely clever. And I have not seen a case where that happened. Basically, it depends, of course, what you mean by accuracy, right? If you're loosened or your accuracy bound to 50%, yes, you can get it all, perhaps. But if you tighten your accuracy bound to 10%, then it's going to be very difficult to get it all. Okay, so let's talk about these things. Basically, speed is how fast the simulator runs. It's usually measured in different ways, but one way is, for example, what is the slowdown of executing a program compared to a real system? Pick your real system. It could be an existing system right now, right? And the slowdown may be 1000x, 10,000x, 1,000,000x, right? If it's 1000x, you can actually imagine running, assuming you designed a full system simulator, if it's 1000x, you can imagine running a real system on your simulator, potentially, right? It'll be dog slow. It'll be really slow, but you could imagine doing that. And some simulators, you can potentially do it, right? Or you can measure it in terms of how many instructions per second your simulator can execute, on average, of course, or how many cycles per second can your simulator model. Okay. I will here also mention that something that I don't normally talk about, which is the difference between functional simulation and microarchitectural simulation. So far, what I'm talking about is microarchitectural simulation. Basically, you model how the underlying hardware behaves, what the latencies are. If your cache takes 5 cycles, 7 cycles, 8 cycles, 10 cycles, you model that. And as a result, you get a metric of performance of what you would expect if you actually design your idea in a system that you imagine, right? But that's microarchitectural simulation that gives you performance energy numbers. But there's a totally different side of simulation, which is functional simulation. This is also called emulation sometimes. I don't like the word emulation necessarily, but basically I like the functional simulation better. So what does this mean? This means that you just simulate the functionality. You don't go into estimating performance, energy, reliability, etc. You just simulate whether the functionality, basically you get a stream of instructions, let's say in an ISA. You just simulate the functionality of those instructions. Now, this is clearly simpler, right? Basically, I think of this as implementing the ISA in a functional level without modeling any latencies, etc. So you get an ad, you basically functionally emulate what the ad does. You basically need to keep a register file, you need to keep main memory, and you need to basically update the register file and update the memory, update the program counter, and that's all you need actually. This is also called really truly architectural simulation, meaning you don't go into the implementation issues. You basically look at the software hardware interface. Now, this functional simulation is nice because it's fast, clearly. You could use it as an emulator. Well, it's much faster, let's say. It's not necessarily fast because you're emulating, you're simulating things in software potentially. But it doesn't give you enough information about clearly what would your performance be, what would your energy be, etc. But usually you need to do this functional simulation anyway whenever you're designing a microarchitectural simulation, because you need to ensure that your microarchitectural simulator is functionally accurate. This is one way of checking at least the functional accuracy of your simulator. You actually have a functional model. Let's call it the golden model. You verify that that golden model exactly obeys the instruction set architecture manual, and you basically execute instructions on that golden model, and that gives you the architecturally correct results. And underneath, you need to also have a timing simulator, let's say, where you actually model the timing, energy, costs, etc., of different design decisions that you make. So these two pieces are very different: functional simulation and timing simulation. And normally, if you want to have a good simulator, you need to have both of these in the end. But so far, what I've been talking about is really more about the timing simulator than the functional simulator. But keep this in mind, functional simulator is also very important. So clearly, the timing simulator is going to be much slower because you model some timing in some way, in addition to the functionality. Okay, so with that aside, let's pop the stack. We were talking about speed. Speed is how fast the simulator runs. Flexibility is very important, especially if you're doing design space exploration, but also if you're fixing bugs, etc. How quickly one can modify the simulator to evaluate different algorithms and design choices. This goes back to the art of software engineering. If your software engineering is good, you would get high speed and high flexibility at the same time, right? If it's bad, then you may actually get neither, which is clearly bad, right? But flexibility is good because you can evaluate many different design options with relatively low cost in terms of the time required to modify your simulator. If your simulator is not flexible enough, then you may not be able to make the design decisions fast enough. So this also goes into time to market. Sometimes actually, because you don't have a good simulator, you don't evaluate a lot of the design space. As a result, you may actually have a subpar product. Okay, so flexibility is also very important. It's a bit more difficult to quantify clearly than speed. People sometimes quantify it in terms of lines of code. How many lines of code do you need to modify? Or time it takes to do some simple tasks or maybe difficult tasks. But neither of those are good enough, let's say, because lines of code clearly have some correlation with the difficulty, but that correlation is not a perfect correlation. You may need to modify 1,000 lines of code, but they may be easy lines. On the other hand, if you have a non-flexible simulator, you may need to modify only 10 lines of code, but it takes all the time in the world to figure out which 10 lines of code to modify. Okay, this goes a lot back to software engineering, if you're taking course in software engineering, for example. Okay, and the last but not the least one is the accuracy of the simulator. basically this is the metric that specifies how accurate the performance or energy or whatever metric you're examining, numbers the simulator generates are compared to a real design, simulation error. Of course, what is real design is questionable here, right? Again, because this is the design that you have imagined. But assume that you have this ground truth, that's the accuracy. Usually you get the real accuracy numbers after you implement the real hardware. So unfortunately, the architect doesn't have the luxury to have access to real accuracy numbers, unless they're doing a very small tweak to an existing processor. But if you're doing design space exploration, if you're doing research, trying to change the paradigm, look at processing in memory, for example, tough luck. You don't have access to this real accuracy number until some example system like what you're imagining is implemented. Then you can evaluate how good your simulator is compared to that real design. Okay, so that's the trick here. Clearly, you can evaluate speed without having access to that system. Well, again, slowdown, usually you would like to try to compare to the slowdown of the system that you have in mind, but not necessarily, because usually you have a good idea of what the speed would be in an absolute manner, right? This simulator is like a dog. It runs like a dog. I can tell you that by simulating things. I don't need to have the real system that the simulator is modeling to tell you that the simulator runs like a dog or it's fast. Right? I can also tell you that the simulator is flexible without having access to the real system that the simulator is trying to model. But accuracy, no. I have to have some access to the real system that the simulator is trying to model so that I can tell you the simulator is this much accurate. And this is where things can get seriously wrong if you're not careful about how you model things. And that's why designing simulators is a really important part of the job of an architect, but an important art also. You need to be very methodical. You need to be very careful. You need to ensure that you're not fooling yourself, because sometimes you fool yourself without even knowing that you're fooling yourself, because you don't have this ground truth, as I said. So this requires experience plus a lot of care, basically. Okay. I mean, there are a lot of stories here to tell, but I just realized that I'm on slide 10 and we've spent a lot of time, but hopefully this is interesting at least. Basically, the relative importance of these metrics varies depending on where you are in the design process and what your goal is, basically. So clearly, if your goal is to do design space exploration, you want speed and flexibility, and you want to sacrifice accuracy. And this is also true in research. Sometimes, for example, the reviewers get hung up on the accuracy a lot. You have this cool idea. You're not ever going to be able to get a good number on how accurate your number is, just because what I said earlier. It's just impossible, right? Without having that system. Because how else are you going to get the ground truth? You have to have that system. And clearly, it's unreasonable to expect someone who is doing research to have that system in hand for every single idea that they develop, right? For some ideas, maybe you expect that, but even those ideas are usually relatively incremental, right? But if you have a big idea like processing in memory, almost nobody has the real system that's being imagined right now, right? So think about that. So it's very important to evaluate the importance of these three things depending on the context and what the person who is doing the simulation is trying to achieve. If your goal is to really match the behavior of an existing system, well, maybe you trade off speed, maybe a little bit flexibility. Well, you usually trade off speed, actually. And you sometimes trade off some flexibility, but you don't trade off accuracy. So there, for example, you try to get to as much accuracy as possible and as much flexibility as possible, but maybe you sacrifice some speed. There are also cases where you want accuracy and speed, but you don't care about flexibility. And those could be the cases where you don't really care about changing the simulator much. You just want the simulator to model the system very, very accurately and very, very quickly, but you don't care about flexibility. You don't care about parameterization, etc. Then you may try to get accuracy and speed, but usually it's very difficult. Actually, speed and accuracy are very much at odds with each other. So that's why I think getting speed and flexibility is easy at the expense of accuracy. Getting accuracy and flexibility is easy at the expense of speed. Now, getting speed and accuracy together at the expense of flexibility is not easy. I've designed a lot of simulators and I modified a lot of simulators in my life, and I can definitely attest to the fact that speed and accuracy go against each other in simulation. Now, if you come out with a great simulator that disproves me, I'm all for seeing that for sure. But this is, as you can see, these are the sort of trade-offs that you need to think about. And again, what you want to trade off against what really depends on what your goal is. So for example, if you're doing early design space exploration, you don't want to have a inflexible simulator. And I've experienced this. One major company, for example, was designing a flagship processor in the early 2000s, actually around that time, even earlier than that. And what they were doing was a very inflexible simulator. The simulator was heavily multi-threaded. Well, that's another design choice you need to make in terms of software engineering, right? Is your simulator multi-threaded or single-threaded? Okay, the simulator was very multi-threaded. For every single thing that's happening in the pipeline, it will launch a new thread. And these threads need to synchronize somehow. And if you got the synchronization wrong, basically your results would be completely wrong. Not only just timing results, but actual functional results would be wrong. So the simulator would actually be giving an error many times when people modified the code. Why? Because they made a mistake in terms of thread synchronization. And the simulator would barf, meaning it would stop saying that, oh, functionally, I've executed something's wrong. Well, why? Because somebody didn't synchronize things accurately. Okay? At least you could catch that if you have a functional simulator that's checking what the simulator executes. So that's the good part, good design trade-off in a simulator. But this is an example of flexibility not being given the importance it should have been given when you're doing early design space exploration. And as a result, this flagship processor was delayed for some time, and eventually a really master software engineer, let's say, owned the code and they rewrote it and they made the simulator good. And as a result, the company was essentially able to deliver the processor in the end, as opposed to delaying it indefinitely, let's say. Okay, so I've given you one example of combining functional and timing simulation. Do I really want to do this? I don't know. Can I make myself the host again? But I don't want to do that back. But let me describe it at a high level over here. So normally when you design a simulator, you have the functional part and the timing part, as I said, right? The functional part executes instructions and timing part determines timing. And sometimes timing and functional parts actually interact. For example, you're modeling branch prediction, right? If you're, whenever your branch predictor says go down this path, it may take you to the wrong path, and the functional simulator can be steered toward that wrong path. And the functional simulator, if you have a golden functional simulation, you know that you're on the wrong path, right? Whenever you're simulating in the timing simulator. So the timing simulator is on the wrong path. Functional simulator is on the wrong path also, because the branch predictors mispredicted things. But you know in the functional simulator that you shouldn't have gone that path, okay? Now this is very important. This enables you to do ideal studies. Basically, the functional simulator, because you know how the program should really execute architecturally, and you know whether your branch prediction is accurate, that branch prediction is part of the microarchitecture, it makes a prediction, and you know whether architecturally that prediction is correct, you basically can tell whether you're on the wrong path in the timing simulator and the functional simulator. Now, this is how you can catch bugs also. So this enables you to do two things. You can catch bugs. For example, if the timing simulator, a microarchitectural simulator, never recovers from the branch, you can say, oh, I'm on the wrong path for millions of instructions. I haven't finished a single instruction in the functional simulator. Something is wrong in the modeling part, timing model part. So I'm going to barf, meaning I'm going to stop the simulation and say, you're doing something wrong because I haven't finished a single instruction architecturally for a million instructions. And you know why? Because your timing simulator mispredicted this branch. And I know functionally that that branch should have gone the other way. So you can design your simulator to have these balances and checks. And that's very important as an architect, to have these balances and checks. checks and balances are important everywhere, but clearly it's important when you're designing systems. Okay, so that's one thing you can do. Having this functional versus timing split in simulation enables you to figure out when you do something wrong in your modeling. But it also enables you to do ideal studies. What does this mean? Okay, you have this functional simulator, you have this timing simulator. This functional simulator quickly executes instructions earlier. Whenever you get to an instruction, for example, you can evaluate what would the architectural results of that instruction be. You don't need to evaluate timing for that because this functional simulator really implements the instruction set architecture, and you don't need timing to implement the instruction set architecture, as we know from architecture versus microarchitecture distinction, right? So this functional simulator can tell you, okay, this branch should go this way. So now you can actually implement a perfect branch predictor, for example, because your functional simulator is executing beforehand. And basically you feed instructions into the pipeline based on what your perfect branch prediction should be, meaning 100% accurate. You should always go into the direction that your functional simulator tells you. Of course, if your functional simulator is wrong, you have a problem, but usually you can much more easily verify your functional simulator compared to the ISA specification. So you can do ideal studies that look like this, basically. You can still model the delays in the pipeline, the data dependencies, etc., but you can model perfect branch prediction. Okay. So you can eliminate data dependencies also. You can see what happens if you eliminate data dependencies because you can keep track of data dependencies in your functional simulator and get rid of them before you feed things into the timing pipeline. So you can play a lot of tricks by splitting your simulator between functional and timing parts. And again, this has implications in terms of speed, flexibility, and accuracy, of course. But usually the way simulators are implemented today are they're split between functional and timing parts. Okay, so I'm talking a lot about concepts that go into simulation. Hopefully these are interesting. Some of these concepts are implemented in your labs. Some of these concepts are not implemented in your labs. So some of your labs, for example, don't have the timing functional part. They all have the timing part clearly, but they don't necessarily have the functional part. Some of them can be trace-based, as we will talk about with RAM later. You can actually get traces of instructions, traces of memory accesses, etc. Some of them can be execution-based. That's another trade-offs in simulation that I'm not going to go into right now. But let's talk about trading off speed, flexibility, and accuracy a little bit more, because this really goes to the heart of simulation. Speed and flexibility clearly affect how quickly you can make design trade-offs, as we've discussed. Accuracy affects how good your design trade-offs may end up being. It also affects how fast you can build your simulator. There's simulator design time and simulator modification time as well. Flexibility also affects how much human effort you need to spend modifying the simulator. And you can trade off between the three to achieve design exploration and decision goals. And as I said, your goals may be very different. And I've already talked about the different kind of trade-offs you can make. But always keep in mind that speed and accuracy go against each other. They're at odds with each other. So let's talk a little bit more about high-level simulation. Basically, the key idea in high-level simulation is to raise the abstraction level of modeling, to give up some accuracy, to enable speed and flexibility. And of course, hopefully quick simulator design. The key advantage is what we've discussed earlier, but it also has disadvantages, as we discussed also. Basically, the hope is that you can still make the right trade-offs and can do it quickly. All you need is to model the key high-level factors. You can omit corner case conditions. For example, let's pick a workload that doesn't get a lot of page faults. And maybe you're really designing your system such that it operates best without page faults. And you're banking on not having a lot of page faults. Maybe you don't do the page fault modeling in your simulation, right? At least in the initial part of your modeling. Maybe you go into the next level, you do the page fault modeling. Okay, you don't model the page faults. The hope is that you still get good accuracy. How do you actually check for that? Well, in your simulator, you add a counter that says how many times a page fault should have happened, but I didn't model it. This is very easy to do. Hopefully, you know the conditions under which a page fault should happen and should be modeled. Whenever that happens, those conditions happen in the simulator, you increment a counter. This counter can be called potential page faults or page faults that I did not model, right? if that counter, let's assume that you execute your workloads. Okay, what you can do, you can, let me not go further. You execute your workloads and you check the counter in the end. If your counter is always 0, well, what you did was a win-win, right? You didn't need to model what you didn't need to model, which is good. Basically, you did the right thing. You got accurate results, at least with respect to the lack of page faults, by not modeling page faults. So you saved a lot of time for yourself. Okay, you look at the counter after you do a lot of simulations, and you figure out that, or some sample simulations, let's say, you figure out that that counter is 10 times out of 1,000 instructions. This is also called MPKI, or PKI, let's say. 10 page faults per 1,000 instructions. Now, if that's the case, probably you were wrong in not modeling the page faults, right? Because 10 out of 1,000 is a lot. Well, 1 out of 1,000 is a lot also in case of a page fault, right? Because a page fault can take microseconds to service depending on the software, right? Then you can say, okay, I did wrong. I should model the page faults. Then what do you do? Well, what you can do in that case is maybe not model the page faults in a lot of detail, right? Because maybe it's not happening a lot. Maybe you're not going to optimize that part of the system as much. You're going to assume some latency for it, right? You can say a page fault is going to take 10,000 cycles. And whenever I get to a condition under which a page fault should be taken, I stall the pipeline for 10,000 cycles. This is very easy to do, right? You don't do anything for 10,000 cycles. You increment the cycle count by 10,000, let's say. Of course, it may not be that easy, depending on how you do your simulation, but it could be as easy as that in your simulation. That sounds great. And that's a very good way of modeling events that you're not going to optimize, and that may not happen very often also, right? So this sounds beautiful. This way you didn't omit the condition that you didn't believe was corner case based on evidence, and you still did some modeling, but you didn't go overboard in modeling, okay, every single thing that needs to be done whenever you need to handle a page fault, all of the requests. You just basically assume 10,000 cycles. Of course, is this accurate? No, it's not perfectly accurate. Why? Because you didn't model everything that goes on in a page fault, right? Well, what goes on in a page fault? When you actually need to handle a page fault, you need to do a context switch, and that context switch brings in some other instructions into the instruction cache, into the pipeline. This is the page fault handler instructions, and that page fault, it flushes your pipeline, everything else gets out clearly, unless you have multi-threading. Okay, we're not going to go into that detail. Clearly, multi-threading enables page fault handling in a much nicer way, because in some other thread, you can execute the page fault handler, right? But okay, it doesn't matter. Your page fault handler needs to go into the pipeline, and it needs to execute. It needs to bring in cache blocks into the L1 cache, L2 cache, L3 cache. It needs to access the memory scheduler to bring in all of those translation structures, all of the needed page table entries. It needs to do the translation. So it actually causes pollution. I don't want to call it pollution, but it actually brings data or metadata into the caches that could evict other data. So we clearly didn't model all of this when we said all a page fault does is increase the cycle count by 10,000 cycles. Yes, you didn't model, but maybe you're still not that bad in terms of your accuracy as well as speed, right? It depends on how important it is. And then you can still add counters, right? You can say, okay, I didn't model all of this, but I expect, based on real calculations, that a page fault on average brings in 5 cache blocks to the L2 cache, 3 cache blocks to the L1 cache, et cetera, and I can count them. And if those numbers become too much, then you decide, okay, maybe I should go and model this page fault a little bit more carefully, right? So that's how good simulator design, in my opinion, usually works. You model some basics for some things that are especially potentially corner cases, and potentially not easy to model. And believe page faults are actually not easy to model. Let me put it that way. Then you go and add the right checks to see if you're doing something wrong in your modeling. Not necessarily wrong, but if you're doing something that could significantly affect your accuracy. And then if your checks actually fire, meaning that they're above some threshold, you go and model in a little bit more detail. So this is, you can think of this as progressive refinement of your simulator. You start with a high-level simulator, progressively you refine it to be lower level, but you never go as low level as RTL in this case. Well, you could actually. You could start with very high-level C blocks, and then you say, okay, I'm going to model this, model that, model that. And over time, you transition your C-level simulator to RTL simulator part by part. Right? Of course, this requires even better software engineering. Basically, some part of your simulator can be modeled with RTL. Some part of your simulator can still be modeled in C. Some other parts can be modeled in Python, etc. And that way, you can actually focus on the parts that you really care about in the design of your processor potentially. Okay, so I took more time here to give you the tools that are available to you, but I think it's important. The key advantage is still high-level simulation. You can omit corner case conditions, but again, while you're doing that, you should be careful. And I gave you also an example of how you would model things at a high level, right? Page fault, 10,000 cycles. In fact, okay, I'll tell that story in the disadvantage, because if you do that, page fault, 10,000 cycles, you could also be fooling yourself. So I'm going to talk about that actually. Okay, the other advantage, which is a sub-advantage of the first one, is all you need to get correct is the relative trends, not exact performance numbers. Because if you're doing high-level simulation, probably you're doing it for design space exploration or a big research idea. You want the relative trends of idea X, Y, Z, T, Q, and you want to be able to accurately compare these ideas with some error, of course. Exact performance numbers, 1%, 2%, 10%, maybe doesn't matter. Okay, maybe some thresholds matter. Okay, if this idea is 5% better than this other idea, I will take it. That matters, sure. That's why your error needs to be bounded somehow, and that's where the art comes in, of course. But you may not care about a 1% difference between idea X and Y, and you say basically 1% difference, I don't care, I'm going to pick the simpler idea. That's how usually things work. If the idea is 10x, well, now you have to think about whether you implement that idea, because the simulation tells you 10x. Assuming your accuracy is good, maybe processing in memory is a good idea to implement, right? Okay. Clearly, there are other design decisions that go into whether or not it's a good idea to implement, but at least your simulator tells you 10x. It doesn't tell you 3%. Okay, so a disadvantage is what we've discussed earlier. Basically, high-level simulation, I mean, you also get this in the lower level, very detailed simulation also. You can still make wrong decisions in the lower level simulation, but high-level simulation increases the opportunity or danger, let's say, of potentially making wrong decisions, because you're far away from the exact how the exact hardware would behave if you modeled everything extremely accurately cycle by cycle. So basically, sometimes this RTL level simulation or very low level simulation is called cycle accurate simulator. Basically, you model everything that goes on in a cycle. Not necessarily everything. You can still basically model everything cycle by cycle, but you still model every single cycle. Whereas here, higher level simulation, you can aggregate cycles, right? If something takes 5 cycles, you increment the cycle count by 5, let's say. Okay, something like that, basically. Of course, it doesn't work in every single case, but you can do this. Of course, the disadvantage is you open up the possibility of potentially wrong decisions. And this actually happens. This is real. That's why I've been telling examples of how you could potentially avoid this disadvantage. So let me give you a story. One of the very famous computer architecture simulators that was very popular in research in late 1990s and 2000s. It's called Simple Scalar. You can actually search for it. It had a terrible way of modeling main memory. Let me tell you the way. Basically, whenever you had a memory access, the memory access was modeled to take memory cycles. And memory cycles was a configurable parameter. And by default, I think it was 50 or 100, let's say, which was very low. Like, okay, it was some number, let's say 100. So you would basically increment the cycles by 100. Now, hopefully you all know that that's a terrible thing to do based on all of the memory lectures that we have discussed, right? Basically, if you're doing anything related to memory, the simulator was useless. And people used it for doing stuff related to memory, hopefully with some modifications, but not always, unfortunately. So clearly, doing that way, let's say you basically increment memory cycles by 100, doesn't model bandwidth. Maybe it doesn't model parallelism depending on how things are happening. So you may be actually assuming an infinite bandwidth memory. So if you're doing prefetching studies, for example, you can prefetch all you want, because the request will be complete after 100 cycles, no matter how many requests you have in the system, right? So this is a bad way of modeling, and it's a bad way of modeling because clearly this is not a corner case. You access memory very often, and this is something you cannot afford to get wrong. So there have been a lot of papers actually that were published using the simulator that had this unfortunate behavior. Later they improved it, of course, but the first version of that simulator had this unfortunate behavior of basically servicing every request in 100 cycles, or whatever configurable number that you decide to put in was. And as a result, I believe a lot of the numbers that were published was actually garbage, let's say, let's say the least. If you're lucky, maybe it was okay. But especially if you were doing something related to memory. If you were doing something in the core and everything fit into your caches and the program doesn't access memory often, okay, this may be fine, assuming everything else is modeled correctly, right, accurately enough. But once you start accessing memory a lot, then you have a problem. Then you need that counter saying, how many times am I accessing memory? Is it more than one time per 1,000 instructions? If it is, then maybe I should model memory more often. And unfortunately, there are many workloads that where a memory access happens more than one times every 1,000 instructions. In fact, in some workloads, like what we've discussed, the streaming workload is a workload that's very bandwidth intensive, right? It happens more than 600 times per 1,000 instructions, right? Not a good idea to model memory with just incrementing a cycle count for a request if you're executing a workload that doesn't fit into your caches, basically. Okay, so this is a real case, basically. So as an architect, you need to be very careful. And as a user of a simulator, you also need to be very careful. If you're taking an off-the-shelf simulator, for example, and basically you need to question, you need to think critically. You cannot just take a simulator off the shelf and say, okay, this simulator, everybody else uses it, now let me use it and get some numbers. You may be fooling yourself, you may be fooling your customers, and you may be actually in the end producing garbage as opposed to producing something useful, right? So this is always the case. Don't treat your tools as a black box. This is actually more general than simulation. If you're using a tool, and if you're an intelligent person, don't treat that tool as a black box. Try to understand what's going on. Try to understand the error bounds. Try to understand what it's modeling and what's not modeling, especially the things, especially within the context of what you're trying to achieve with that tool. Because not every tool is designed to do everything really well, right? Even in the domain of its expertise, let's say. I mean, clearly this particular simulator that was used by, I don't know, hundreds, if not thousands of researchers was doing something terribly wrong in terms of memory, for example. And as a result, a lot of wrong decisions have been published, if not made. Let me put it that way. Okay, so keep this in mind. Whenever you're using a tool, keep this in mind too. You need to think critically. You need to go inside the box a little bit, as opposed to thinking that it's a black box and trusting the black box. Okay, so basically, this opens up the possibility. High-level simulation clearly opens up the possibility of potentially wrong decisions. Then the key question is how do you ensure you get the relative trends accurately without making those wrong decisions? And this is where an architect's art and experience and care and meticulousness comes in, basically. Okay, as I said, simulation is actually progressive refinement also. Usually what happens is, this is actually true for, as far as I know, almost all companies that design hardware, that do real designs, basically at the bottom over here. You start with, and also some software. If you're designing a very complex piece of software, for example, a memory, an operating system, you may actually decide to simulate an abstract model of your operating system scheduler, memory allocator, etc. first before you go into the real design. So the ideas are actually applicable to software design as well, not just hardware design. But I'm giving you examples from hardware design. Whenever you're designing hardware, you usually start with high-level abstract models, C-level models, like what you've been doing in the class. Sometimes you're even more high level than what you've been doing in class, actually. Over time, you progressively refine the model to create medium-level models that are less abstract. You could potentially write this medium-level models from scratch based on the learning from the high-level model, or you could actually adapt the high-level model gradually into the medium-level model. Clearly, there are trade-offs associated with it. Sometimes you may decide to actually write it from scratch because the high-level model accumulated a lot of clutter, let's say. And sometimes rewriting from scratch is a good idea. Okay. And then over time, here you make some design decisions, and then you decide, okay, I'm going to model these parts more accurately because these parts are more exercised by the workloads, etc. And my design decisions are more going to be on the processing and memory side. So I'm going to model the memory controller very accurately, etc., etc. Then you create a medium level model that's less abstract, that's modeling the right things that you believe should be modeling based on evidence that you gathered with the high level model and the workloads. And then over time, you gather even more evidence. Say you make some of your design decisions even more concrete, and you transform your medium level model to a more lower level model. Let's say RTL is the lowest level model with everything modeled, of course. So that's the closest to the real design. And over time, you say, okay, my RTL is working fine. I don't have bugs as far as I know. I can verify it. I can validate it, etc. Now let me go into the real design. And then you give the RTL to layout engineers or automated tools that actually produce the real design. Okay, so that's your progressive refinement over time. You can go from a very high level simulator to a real design step by step, of course, while ensuring that you make the right design decisions, hopefully, along the way. Okay, so there are interesting things to examine here. Of course, once you have the real design, as I mentioned, you can go back and fix the low level models. You can make them more accurate with respect to the low-level design, real design. You can also go back and fix the medium-level models and high-level models to make them more representative of the real design. You can reduce the accuracy. Basically, once you have the real design, you can compute the accuracy of everything that's above, because you now have the ground truth, assuming that the real design is implemented correctly, which is a different question, of course, right? You need to verify and validate the real design also. But assume that it's implemented correctly, then you go and validate. You go and compute the accuracy of all of those models, and you can decide and go back. You can refine all of these models. So refinement works both top down and bottom up. Bottom up happens, of course, when you have the real hardware design, right? So, okay, there are some trade-offs also here. As you refine, meaning go down above the list, basically go from top down. Abstraction level clearly reduces, right? In a real design, your abstraction level reduces. Accuracy hopefully increases. Hopefully, as I said, it's not necessarily true if you're not careful. Sometimes a high-level model is much more accurate than a low-level model if you're not careful. I mean, this is usually true actually between high-level and medium-level models. Once you go close to RTL, you're hopefully careful at that point in time. But if you're somewhere around here, your high-level model may be more accurate. And this is usually true in energy modeling, for example. I've dealt with a lot of energy models in my life, and sometimes, especially when you're at a high level, the less you consider may be better. If you consider just a few parameters that make a big difference, that may be much better than considering a lot of parameters, basically. Why? Because just those few parameters are much more accurately potentially estimated in simulation compared to thousands of parameters that go into your energy. And one of the key parameters is how many instructions you execute per cycle, for example. That's a very good estimator of energy. If I have to pick one thing to estimate my dynamic energy, I would pick my instructions per cycle. Clearly that's not the only thing, but if I had to pick one thing, one parameter to estimate my energy, that would be my instructions per cycle. Now, this is an example. If you cannot model everything accurately, clearly I would pick a higher level model. Okay, this is an example of accuracy not increasing as you go from top down. Well, hopefully with real design, your accuracy is 100%, right? Assuming you've done everything right. Okay, flexibility reduces going from high level to real design. Well, clearly, right? Because high level, you can hopefully, I mean, assuming you've done everything right, of course, right? You've designed a very flexible simulator to actually do the design space exploration. But as you progressively go down, real design is not flexible anymore. Well, unless it's an FPGA, which is a different kind of flexibility, okay? And speed likely reduces except for real design. So clearly your speed is fast here. As you add more modeling to your simulator, it becomes slower. As you go into RTL, it becomes like a dog. You cannot execute even more than 1,000 instructions, etc. Well, you can, but it takes a long time. Once you go into real design, it becomes fast again, right? Because why? Now it's you're running real programs on real hardware. You're not simulating anymore. So there's this interesting gap between very low level models and real design. Real design clearly can execute things faster because it's real, whereas it's not doing simulation. But of course, maybe you don't care about that. I mean, you care about the speed of it, but you've lost the battle of simulation anyway once you went into the real design. You don't care about simulation maybe at that point, right? Okay, and as I said, you can loop back and fix higher level models. Once you have the real design, you can loop back and fix, and maybe sometimes actually you can have smaller feedback loops. If you have a good low level model, that's RTL, once you implement a block, you say, oh, I forgot this particular thing in my medium level model. That's why it's not as accurate as I expected it to be. So I'm going to fix my medium level model. So for example, in the page fault handling, I designed my page fault handler, page walker, etc. In my low level model. And it says that I need to really model 10 memory accesses with every page fault. You go back and fix your medium level model to model 10 memory accesses. And maybe you don't care which 10 memory accesses they are. You just want to ensure that those 10 cache blocks that otherwise belong to the executing program are evicted from the caches. And the bandwidth of those 10 memory accesses are modeled. You can actually have an abstract model that models 10 memory accesses without going into a lot of detail on how those 10 memory accesses exactly occur, right? Okay, so that's one example of how you can fix a medium level model by with the learnings from a low level model. Okay, so hopefully this is interesting. I find this fascinating because I enjoy actual simulation a lot, and I've written, for example, my PhD thesis on run-rate execution, which we briefly mentioned. I actually modeled it on 5 different simulators, both academic and industrial, and I've seen examples of many different simulators, many different trade-offs, and it went into real hardware also. So it actually went through all of these phases, if you will, and it's very interesting to see with experience how these different models actually behave. Okay, so making the best of architecture, in my opinion, a good architect is actually, in the end, comfortable at all levels of refinement, basically including the real design, all the way from high-level models to real design, including the extremes, basically. A good architect, I think, knows when to use what type of simulation, and that's an art, as I said. With more experience, you become better, of course, and with more keen insight, you also become better. That's why I think architecture is a lot about insight and trade-offs and how to make them. And this is another example of a trade-off and evaluation, how to evaluate things, right? And of course, more generally, a good architect really should know what type of evaluation method to use when. And recall that a variety of evaluation methods are actually available. Theoretical proof, analytical modeling, simulation with varying degrees of abstraction and accuracy levels, prototyping with a real system. FPGAs pose a very good construct today, but any kind of programmable system that can enable you to prototype your idea could help. But of course, real implementation too. So with that, let me go into an example simulator. I think I'm going to take a break at the end of this longer than expected lecture, and then we're going to resume. But let me go into continue the simulation lecture. Any questions so far? I think you all are silent. Either I'm hammering you with going very fast, or this is really interesting, or people are already zoned off. It'd be good to get some feedback or some questions. Okay. Feel free to ask questions. I think we're done with the most important chunk of the lecture. But in the rest, I'm going to talk about a memory system simulator that you're actually using. This is Ramulator. And this is a simulator that actually grew out of original simulators that I myself and my collaborator, Thomas Moshibroda, had written in C# when we joined Microsoft Research in 2006. And we wanted to write memory controller simulators that could enable us to evaluate memory scheduling algorithms and memory performance attacks, etc., in a nice way. Clearly, you've seen a lot of those papers, so I'm not going to go into them. But this simulator evolved into what is called Ramulator right now, which is an open source simulator that's used widely by industry and academia. So industrial groups at Google, Intel, Microsoft, Apple, and other places have been using it, and many academic papers have used it actually. They've actually enhanced it much better. And of course, my students over time made it much better also. But essentially, when we released Ramulator, our motivation was very different from when we initially started writing it. When we initially started writing it, it was first not called Ramulator. It was called Fair Mem Simulator, actually. And the goal was really to evaluate the effect of different memory scheduling algorithms on performance and fairness. That's it. But over time, this simulator evolved into something totally different and hopefully much more useful, in my opinion. And essentially, the goal was to actually have a flexible, easy to extend simulator that can model many different types of DRAM and memory controllers. That's the idea. And we've discussed this already. DRAM and memory control landscape has been changing. There are many new and upcoming standards, processing in memory being one example of them. There are many new controller designs. And a fast and easy to extend simulator is very much needed. And I've shown you this table before. So what is Ramulator? As you've been experiencing, hopefully, it provides out-of-the-box support for many DRAM standards. This is a list over here, but new versions of Ramulator have come up after this slide was made. So you can actually see Ramulator providing support for some other academic ideas also. But clearly, it's a simulator that can simulate many different types of memory. It's actually, at the time it was released, I don't know how it is now. Somebody needs to do studies probably. It was much faster than the fastest open source simulator, 2.5x, as you can see. It was the only modular and extensible simulator to different standards. And other people took advantage of it for various studies, clearly. There's a version of Ramulator that actually models emerging memory technologies as well, which we will talk about in the next lecture. So it enables studies that look like this, basically. You can compare different DRAM standards. And this is an original initial study from Ramulator that enables you to compare, I don't know, how many standards are here? 8, 9, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different DRAM types. And you can plot graphs that look like this, basically. So this is average across 22 workloads, very simple CPU model. So CPU modeling is also important, and Ramulator has a very simple CPU model that you can use for very simple, quick studies, quick and dirty studies, let's say. And this graph basically shows the performance improvement, normalized instruction per cycle to DDR3 standard with different types of memory used in each of the workloads. Well, each of the workloads, all of the workloads are represented using this violin graph, if you will. These are the speed ups that DDR4 experiences compared to DDR3, for example. And in this case, it happens to be high. Later, we actually found out that there are other workloads that do not get speed up from DDR4. In fact, they see slowdown, for example, as we discussed also. But these workloads happen to actually get some speed up. And this is the highest speed up that you get. This is the lowest speed up that you get compared to DDR3. And this is the shape of the distribution. You can see that most of the distribution actually lies here, which is similar to not getting a lot of speed up, as you can see. So this actually shows you potential performance improvements that you would get, for example, with different standards. A study that you could otherwise not do with any other simulator, because no other simulator has support, out-of-the-box support for this. And simulator also has, Ramulator also has support for easy to extend extensibility to different standards. So if you want to add your own standard, it's relatively easy in Ramulator, for example, compared to some other simulator. Also, you can see that high bandwidth memory is doing really well, for example, for a good fraction of these applications. So in fact, it's probably the winner over here in terms of what kind of performance it provides on average. This is the average bar, the blue bar over here compared to DDR3. Okay, so you can do this sort of studies basically with this kind of simulator. And Ramulator is still reasonably cycle accurate actually in the memory part. In the memory part, it models timing parameters. Maybe it doesn't model all of the timing parameters, so that's where the inaccuracy comes in. But for a good chunk of the important timing parameters, they're modeled. As a result, it's reasonably accurate. This also shows that LPDDR3, for example, loses performance, right? LPDDR4 also loses performance slightly compared to DDR3. This is the average. You can get 8% performance loss on these workloads. So as I said, this is very much workload dependent, and this is very hard to model in some other way. If you come up with an analytical model that can distinguish between these memories, that'd be great, but it's not an easy task to actually do. And if you're interested, this is the Ramlater paper, and this is a bonus review as part of homework 4. I don't remember actually if we actually assigned it for homework 3. If we actually assigned it homework 3, and if you didn't do it, you can still do it as a bonus assignment for homework 4. It's only a 4-page paper. I'd recommend reading it because I think this is an example of computer architecture combined with good software engineering, refactorability of code. Of course, things can be made even better. I believe Ramlater even also deserves a critical eye in terms of making things faster and better and more scalable. But I think it's good to understand how it works. And it's all open source. As I said, it's being used by many people. And you're using it for your assignment as well. So why not actually review the paper too? Okay, I've already talked about the study actually using Ramlater. I'm not going to go into more detail, but remember the study where we talked about demystifying complex workload and DRAM interactions to motivate memory latency studies. Basically, one of the key observations here was new memory technologies do not reduce memory latency. As a result, some workloads suffer. That was the key conclusion. I described the study in the low latency memory lecture to give a concrete example of why memory latency is really important to look into, because the lack of focus on memory latency is actually causing us to lose performance in important studies today. But I'm not going to go through this in detail. We've already covered this in the low latency memory lecture, but I will focus on one thing that's very important. Basically, you cannot do this study on a real system. And we've already discussed why, because a real system does not have more than one type of memory, does not support more than one type of memory. That's why you need to do this in simulation. And clearly designing a real system, we already discussed actually some of these evaluation methods when we discussed the study. You could design a real system that supports 9 modern DRAM types. Good luck with that. It's extremely costly, as we discussed. And you would probably be spending a good chunk of the rest of your lifetime to design that sort of system, which is probably not worth the effort because nobody's going to buy that system. As far as I can judge the market, let's say, and it'll be purely your own fun to try to design that system. But clearly, this is an example place where simulation is extremely useful. Analytical modeling is also, as far as I know, I mean, I'm not going to say not possible, but it's extremely tricky in the best case. It's extremely complex and extremely tricky to model the differences between these standards. So analytical modeling is not there. Clearly, we're not looking for a theoretical proof. We're looking for real workload differences in terms of the different behavior. And you cannot do it on a real prototype as well, because real prototype suffers from the same problem we said for a real system. So the only option that you have actually in this study is either simulation or analytical modeling. But as I said, analytical modeling, even with a lot of experience, it's hard to imagine what kind of analytical model you would build to distinguish between all of these different memory types and workload behaviors. That's why simulation is really critical over here. And yet, I also told you the story that this paper was rejected by so-called experts, saying that, why didn't you do the study on a real system, right? So this also shows you how broken some of the review system is, because there's no accountability in the system, right? So, I mean, this is something also you need to keep in mind, because you may need to justify why you're doing simulation, but sometimes you may not be able to justify if the system is not set up for accountability, because this person can reject your idea and you don't even know who this person is because the system is set up that way. Anyway, I'm not complaining. I'm just telling you life is not always fair. Okay, so I'm not going to go through all of this over here, but basically you can see that different types of DRAM exist, and we already covered a lot of this. And with simulation, you can make observations that look like this relatively quickly. You cannot do this with an analytical model that you don't know how to construct, or a real system that you don't know how to build, or you don't have money to build, and you don't have time to build, you don't have patience to build probably. But simulation enables you to explore these dreams, basically. You cannot explore these dreams, meaning the differences, in these different architectures and how these different workloads behave without simulation. And with simulation, you can get insights, basically. Several applications do not benefit from more parallelism that's offered by new memory technologies like hybrid memory cube over here or DDR4. In fact, you lose performance because of the huge increases in latency in some technologies, right? So that's insight, basically. You can generate insight using simulation. And you can basically come up with takeaways using simulation again. And there's no other way you can actually go to these takeaways. And this is just one example. There are many, many. Processing in memory is another example, in my opinion. But there are many, many other examples. Any new idea, some ideas, of course, are more amenable to other types of evaluation methods, but some ideas are much less amenable to other types of evaluation methods. And this is one of those ideas that's much less amenable to other types of evaluation methods than simulation. Processing in memory is another example of this. But you can clearly see you can generate insight that's really important for future, like DRAM latency remains a critical bottleneck. Bank parallelism is not fully utilized by a variety of applications, and spatial locality continues to provide significant performance benefits. If you reduce it, you have a problem. And low power memory for some applications can provide energy savings without sacrificing performance. To be able to get to this insight, you need to design your simulator well, accurately. And actually, this simulator is already open source as well. We open sourced the simulator that you can see, actually, you can click on this. The tools, all of the tools, not just the simulator, but the workloads are also open source. And you can click on this link, but also there's also memben, which is not linked over here, which is the memory benchmarks. You can find it in the paper, basically. If you want to replicate the studies, you can do that using the simulation tools as well as the workloads that are used in this study. Okay, for more information, you can certainly look at this paper. So a remulator for processing in memory actually is another thing that you can use. We've extended it recently for processing in memory. And that actually has enabled a lot of research in terms of processing in memory as well. You can find it in this remulator PIM link if you're interested. Of course, there are some internal tools that we use in my group that are not released outside so that we can actually do the research relatively fast, because whenever you release something, you need to clean up some things a little bit. If you're at the cutting edge of research, you don't want to be cleaning up things and also generating cutting edge research ideas at the same time. You clean up things a little bit after you finish the research and then release things that way. So it's always the case that the internal tools that are used in a cutting edge research group and a cutting edge product group also is internal to the, is more advanced, let's say, compared to the released versions. Clearly, some groups, unfortunately, do not release their open source versions. I think it's really important to release things. That's the scientific way of doing things. Unfortunately, it's not common practice in architecture. That I find very unfortunate. I can, of course, understand why companies don't release things. I wish they did more often. Some companies are better at that, but not all companies are releasing things. In fact, we recently collaborated with Intel to release a cooperative simulator with them. It's called Scarab. It's released online somewhere. I don't have the link over here, but in some later paper, we can actually provide the link. But it's good that some companies are more open to releasing their infrastructure, because that also helps people to compare things and also validate things. So clearly, open source releases is good for scientific validation if you can do it. As I said, I think most people can do it, but they choose not to do it in a lot of studies. But I think that's probably not the right thing to do. I understand why people may not release it right away. And in fact, that's probably a very good thing to do, because you want to verify what you release. You don't want to release a simulator where you increment the memory cycles by 100, for example, because that does more harm than good, perhaps, especially if people use it without questioning. So you need to clean up. That's why there's a lag time in terms of the detail in your simulator, in terms of the advances in your internal simulator versus external release part. But I don't understand why people do not actually release the simulator. There are only very few cases actually where I think things should not be released. Like if it's related to a company, for example, and you have confidentiality requirements, then clearly that's a good case not to release. But if it's academic, I think it's important to actually scientifically release these infrastructures. Okay, if you're interested in remulator for PIM, processing in memory, I think you can take a look at this paper that actually looks at how to use simulation and analytical modeling predict the performance and energy benefits of near memory computing. So this actually talks up more about analytical modeling using machine learning, as I mentioned earlier, as a good path for future. Okay, so what we discussed, so I'm going to finish relatively soon this part. Basically, what we discussed is actually applicable to other types of simulation as well. I will very quickly talk about COVID-19 spread modeling and prediction. This is another example, I think, where experience and system simulation can prove very useful. Okay, there's a raised hand. Let me see. Fabian, please go ahead.
Yes, I have a question about the remulator before we move on.
Yeah, sure. Go ahead. If I can answer, I'll try to answer.
Okay, great. I'm wondering, how did you verify that remulator does the correct thing? I saw in the paper something about a trace, or then you compared it to a model, but I didn't quite understand how you did.
Exactly. So that's a very good question. I think, this has been a while, but the way we verified remulator, I can go back to remulator. I mean, I don't need to go back because it's, I don't think it talks about it. But basically, there's a golden model, let's say, of a memory controller that's released by Micron. Or I don't remember actually. Maybe it was Xilinx. I think it was Xilinx. It's an RTL.
It was Micron.
It was Micron. Okay. Maybe it was Micron. I don't remember right now. Actually, it could be both. I believe in the end we verified both because there's a Verilog model that's released by Xilinx also. But I believe I don't remember in the paper. We could look it up. But released by there's a golden model for memory control that's released by, let's say, a company that's respectable, and we verified that golden model also, and we verified remulator against that golden model. Is it really doing the scheduling right? Is it really obeying the timing parameters? Basically, all of those were verified.
So you somehow saved the trace of the commands or something like that, and then compared it to this golden model.
Exactly. So you actually, you create a trace of commands, and you run it through the golden model, and then you run it through remulator, and you look at the actions that each of them takes, and if they are consistent with each other, then, and assuming the golden model is correct, of course, and remulator is also obeying what the golden model is doing.
All right, I see. Yeah.
And that's a good way of verifying the simulator, assuming a golden model exists.
Yeah, it's just in the labs I experience it's quite hard to find errors in a simulator.
Yeah. So you're experiencing. Go ahead.
Yeah. Actually, Atlas is not as fast as I expected, and now I'm a bit stuck on how to find where the error is. But yeah.
No, I think so. What you're experiencing is real. Basically, it's every architect experiences whenever they start doing studies. So what you're experiencing is not is normal, I would say. That's what happens in simulation, especially if you're doing simulation for the first time. You may get surprised by it, but that's really how it is, because you're really evaluating some future idea or some idea that is there, and you don't have a golden model. And I actually wanted to set up the same situation that you would have in the real world.
Yeah, that worked out quite well.
yeah, exactly. So I think I'd recommend, if you're having trouble, I recommend certainly talking with the TAs. But
sure.
If you keep having trouble, that's normal. You can document what kind of trouble you had also, and I think that's good. In the end, what I'm really interested in is your learning and how you actually solve the problem, if you can solve the problem. My guess is you will be able to solve the problem given enough time, of course. But basically, I think this is good learning in the end.
Okay. Yes. Yeah. Thanks for the answer.
Sure, you're welcome. And I've experienced this many times actually in real companies as well. And in fact, real companies get stuck sometimes in simulation as well. Sometimes there's an idea that is shown to work in some other simulator. It doesn't work in that particular simulator. All sorts of things happen basically because the system is different, right? And I've actually seen this in my PhD thesis, for example. I evaluated, as I said, my PhD thesis on at least five different simulators. And the evaluation that I've done on basically no simulator matches the other. Let me put it that way. You always get different benefits, let's say. The key is really understanding why. And that why sometimes can take a long time, basically. Sometimes, for example, there's some bottleneck in the simulator that you didn't model in one simulator. And because you didn't see that bottleneck in one simulator, when you go into a detailed simulator, there's a bottleneck. You have to eliminate that bottleneck for your idea to work. For example, I mean, my favorite example with run-ahead is this. Run-ahead execution clearly relies on enabling more memory accesses concurrently, right? And if your processor is not able to sustain more memory accesses than, let's say, some amount, then you won't get a lot of benefit from run-ahead execution. So you need to have misstatus holding registers, enough misstatus holding registers, so you cannot say 4. And I think this was one of the issues with one of the simulators that I started out with, basically. The misstatus holding registers was 4, but run-ahead execution actually generates requests that's much more than 4, let's say 40. So you need to increase the size of some of these structures to be reasonable, let's say. Now, if you've seen the Apple announcement a couple of days ago, maybe yesterday, I don't know exactly. I'm confused about the days, but either yesterday or the previous day, now they have huge structures, right, in their machine. So in that kind of machine, maybe run-ahead execution can be useful potentially, but in a machine that's, in a simulator that's conservatively provisioned in its structures, it may not work well. So in the end, you really need to understand what you're doing and what your simulator is. And that's how you actually really grow as an architect. And I believe that's how I have grown. And I think that's how you really learn being an architect in the end. Because in the end, the devil is really in the details of how you do these things. You may develop an idea, yes. And you may actually be very creative in developing ideas. That's a really good part of being an architect. But now, when it comes time to actually test how good your idea is, unfortunately, there's no, let's say, clean way of testing it. So you have to go through some sort of simulation. Okay, so let me quickly talk about this COVID-19 spread, since this is really important in my opinion. And this is another area where I don't see, unfortunately, very, very unfortunately, a lot of open source models of COVID-19 modeling and prediction. But this is another perfect example of simulation, in my opinion. Basically, you want to take some measures to counteract COVID-19, let's say. How do you actually take those measures? Basically, you have an idea of counteracting COVID-19. How do you assess that idea will affect COVID-19, let's say, infection probability? So there's usually in these studies, if you looked at them, there's this R factor, which is really the probability or probability of infecting someone else, one person probability infecting someone else. And usually if this is less than 1, that's considered that it's good. I don't think all values less than 1 are good, but closer to 0 is better, of course. If it's 0, it's great, then nobody's infecting anybody. If this probability is more than 1, then it's considered out of control, basically. This infection is really out of control. And actually, the values are much higher than 1 today, I believe. That's very unfortunate. So the key thing is to do the modeling to understand how you can, basically, first of all, how you can potentially get this R value to be less than 1. What are the ideas that you implement to get that R value less than 1? I mean, clearly, I believe it's a simulation problem. Let's take a look at all of the possible things that we could do. Well, this is clearly an architectural way of thinking about it, but you could do analytical modeling and estimation, or you could do some simulation also. I think simulation is actually a very good tool here because you could simulate the behavior of, for example, what people would do with different sort of measures. Okay, you don't require anything from people. What do people do? You can simulate based on some of your guesses and based on the best scientific evidence you have, right? Or you tell people you're not going to go out of your houses. What would people do, right? You can model those things and you can see the effect of your measures on this R value. And based on that R value, maybe there are other things that contribute to this R value, right? Temperature is one of them, for example. There's a lot of scientific evidence that show that as the temperature goes down, the infectiousness of this disease increases significantly. This is actually scientific evidence from studies that are done in Brazil, for example, and other places in the world. Actually, there's some Swiss study that's done I believe, I don't know where exactly, but maybe in Wuhan actually. There's a study from Swiss folks who have published showing that you can actually the temperature actually significantly affects things. So you can basically do the modeling in terms of how the temperature is going to change over time, and you can clearly have a good model of this, right, based on past evidence in terms of how temperature is behaving. You can even simulate the temperature, of course, but that's probably an overkill. You can perhaps use some already existing models of temperature. And then you can basically simulate how many people will be infected based on temperature, based on humidity, based on how many people are going to be indoors, based on how many people, how people are going to react to your measures, etc. And you can get a number for your target metric X. And your target metrics X may be, I don't want more than, I don't know, maybe target metric X can be how many people will be infected in your population, right? Because that affects how badly overrun your health system will be, right? I mean, your target, an even worse target metric could be how many deaths will there be, right? I mean, we're talking about real deaths here, unfortunately, and that's happening also. But basically, this is really the scientific method of handling COVID-19, and unfortunately, I don't see much of this exposed. A lot of people talk about economy, but I don't see. I mean, even economy is not handled, in my opinion, in a scientific way. But this is, I believe, simulation is the scientific way of handling this. Okay, let me go a little bit more. Clearly, this is a non-existent system, right? We don't know what will happen into the future. All we can do is predict based on the past and what kind of measures and their effectiveness. In fact, there's a lot of data. If you look at the literature, there's a lot of data in terms of the effectiveness of some of the measures. You can actually go back and look at the measures that have been done by different countries, and you can look at how different measures affect the R value, the infectiousness of the virus. And there are actually some studies that have been published. Unfortunately, many of them don't release their models, but clearly you can get a lot of data based on the past, and you can use that to actually simulate the future. And simulation actually in this case enables the exploration of many dreams. Okay, I don't take any action, what will happen? I require masks, what will happen? I require people to stay at their homes, what will happen? Basically, you can evaluate all of these, and you can actually evaluate the potential of many of these. Clearly, you can help reality check, and you can actually take a wild guess, not a wild guess, let's say, an educated guess based on simulation and based on the best scientific understanding that you have in terms of how many people will be infected at a given point in time, how many people will be dead at a given point in time, how badly will my hospitals will be full at a given point in time. And then you can go back and decide which dream is better. You can potentially do the same thing for economy, but I don't think I have enough knowledge on the economy. But I believe actually public health should be considered normally much higher than economy, because we're really talking about real dead people here. Anyway, simulation, I think in this case also enables the ability to fool yourself with false dreams. So you should clearly, whenever you're doing this COVID-19 modeling, you should be really careful about this also, right? That's why I think validating as much as possible your models based on back data, past data is important. Looking at whether your models actually, if you simulate starting from the beginning, whether your models actually could have predicted what has happened is also important. So back validating is important. So you can actually do a lot of interesting things if you have enough information from the past. So I think this is a very scientific way of approaching, and I think this is a very systems modeling way of approaching. And I think an architect is actually a very good person, if you will, to actually see this sort of systems modeling. And again, goals, well, explore the design space quickly, right? Because you don't want too many people dead, and you don't want your hospitals to be full. Well, because why? Because if your hospitals are full, maybe some other issues will happen, right? Because there are other people who may get sick for other reasons, and if your hospitals are full, you may have other problems. And you can also model those potentially, right? Now, of course, your modeling becomes more complex. And actually, in this COVID-19 spread, you want to do both. Explore design space quickly and match the behavior of an existing system, meaning what has happened so far. your model should be able to predict what has happened so far really well to be a reliable model, in my opinion. And there may be other goals in between, but you can guess that. And again, your model has the same trade-offs: speed, flexibility, and accuracy. You don't want, well, you want your model to be accurate, clearly in this case, but you don't want complete accuracy, right? You want to be just accurate enough to make the right decision, right? You don't want to be able to predict, let's say, exact number of infected people. If it's above some threshold, you care. If it's below some threshold, okay, maybe that's the measure I want to take. You want it to be flexible enough so that you can actually model different types of scenarios, including temperature, etc. And you want to be able to fast enough. Your model should give you a result quickly. In, I don't know, December 2020, if I take measures X, Y, and Z, I will have this many infected people and this many number of people dead. And you want to get that answer, well, hopefully in hours, if not days, right? Clearly, you don't want that answer after you get to December 2020, right? So this gives you an example of modeling and simulation in a very, let's say, important existing topic. And I think, I wish the public discourse in this was actually more scientific as opposed to more dogmatic, let's say. But I wanted to give you an example of how simulation and systems modeling can actually bring something useful to the ground. Okay, all of the same trade-offs exist that we've talked about. We can go into more details of this, but the key is you can potentially still make the right trade-offs in terms of your decision making, but you don't want to be able, you don't want to fool yourself also. So you need to be careful in the end. Okay, I'm going to skip these because these are actually slides that I repeated. You can apply all of these to COVID-19 modeling in some way. And again, I think in the end, a good architect is comfortable at all levels of refinement, including the extremes. And I think a good architect knows when to use what type of simulation. I think it really bothers me that the decision makers are not employing the best techniques for good architecture, let's say. It feels, at least based on what I see, are very bad dogma, let's say, in the at least what's being communicated to the public is dogma as opposed to scientific method and good systems modeling. Okay, I'm going to stop here. I think I've said more than enough, but hopefully this gives you an example of how science can be effective if it's used and if it's respected. If it's not respected, of course, science cannot be effective anywhere. Let me see how much time we spent. Okay, 2 hours, 5 minutes. Wow, this is much longer than I expected to spend. So, okay, let me take, yeah, let me take any questions you have. Any questions on, I guess, this lecture? Because I think what I'm going to do is not start lecture 14B today, because I don't think we're almost 2 hours, 5 minutes. And I don't think it will do justice to the lecture 14B, which is emerging memory technologies. But if you have questions, I can take them for some time. Otherwise, we will, I guess, adjourn early and start tomorrow at the same time.
Maybe I have a question. I don't know if
Sure.
it's too detailed, but
Yeah.
Remulate uses a lot of templates.
Yes, okay.
And this makes compilation quite slow.
Yeah,
so
I agree.
I wondered, why did you pick templates and not something like inheritance? Or
yeah, so this is, I think.
Do you have an answer on it? Or?
I mean, I have an answer, yeah, and I mean, I don't like it as much also, frankly. This was, I mean, the real answer is we picked what my students were comfortable with. Let me put it that way. In the end, the type of thing that's used in any software depends on what the software writer, at least the primary software writer, is the most comfortable with. The original version of Remulator did not have any templates whatsoever. We actually used a lot of inheritance, for example, in the original version, which didn't look like Remulator. Let me put it that way also. I think templates enabled my students to do things easier than they could have done otherwise, potentially, at least based on their knowledge. But I agree that there could be other ways of actually designing the same thing, potentially in a less messy way, let's say. Does that answer your question?
Yeah, now I see.
Okay.
Especially in actions, it's quite complicated in C++, so it makes sense to use templates.
Yeah, exactly. And C++, I think, again, that's a choice what my students were comfortable with also. So for example, the initial version, and actually there is a C# version of Remulator also. You can download it. It's not as up to date as the C++ version, because we believe that C++ would be more used by folks everywhere, because C#, I don't know how much it's used right now, but I don't believe it's as popular as C++. But there's a C# version of Simulator that I believe is cleaner. You can download it and see for yourself, but it's not as up to date, unfortunately. I think actually in my research group, some folks still use the C# version internally. But when we released it outside, we decided we would use the C++ to get more people on board. So that's, again, a very personal choice, as you can see. It really depends on the exposure of the software engineer.
All right. Yeah, but it makes sense. Thanks for the answer.
Sure, you're welcome. Okay, there's another question here. A little off topic, which is fine, I think. Apple presented unified memory technology. How is this different than the DRAM configuration we studied until now? What are the advantages? So that's a great question. And I don't know what actually unified memory technology means, because I didn't really study Apple's presentation as much. I didn't really have much time. I just looked at some pictures. Do you know what it means?
Yeah, I think it's a system on a chip, the M1. So they have the DRAM on the chip, basically, as far as I understand. And I also think they share it with the GPU. The memory is shared. So that's the only thing I know. I just saw the presentation.
I see. Okay. So that's what they mean by unified. It's unified between the CPU and the GPU.
I think so.
Okay. Yeah, I think so. I mean, I have to know more about the details of this, because without knowing, I guess I don't know more what does unified mean. But it makes sense, I think. It makes sense for unified to mean shared between CPU and GPU. My thought is that I don't know if they're using high bandwidth memory. Did they disclose that? Anything related to that?
Yeah, I haven't seen anything.
Okay. So. Yeah, I don't know if they're using 2.5D stacked or 3D stacked memory. It would make sense to me if they were using it, but again, they may not also. But I think in this case, I'm pretty sure they would be using DRAM. In this case, I think that unified memory means that the DRAM is shared between the CPU and the GPU. But again, this is my wild guess based on what you told me at this point.
Okay, thanks.
Sure, you're welcome. Yeah, there's some comments saying that in NVIDIA, as far as I understand, unified memory is a software construct which makes it easy for both GPU and CPU to access memory without explicitly copying it over. Maybe it's the same thing here. So I think it makes sense to me, basically. If the CPU and the GPU are sharing DRAM, I think it makes sense to not explicitly copy data between the CPU memory and the GPU memory because they're already sharing physical memory with each other. This is not an option clearly in discrete GPUs, right? Discrete GPUs have their own memory, which is GDDR5 potentially. CPUs have their own memory. And whenever you want to send some data from a CPU to a GPU, you normally copy data from CPU's memory to GPU's memory and vice versa. But if the CPU and GPU are sharing the same physical memory, there's no need to do this sort of copying. And I think of course, all companies are free to use, let's say, free to assign different meanings to the word unified. So I don't know if Apple is using it in the same context as NVIDIA has been using it, which is accurately characterized by your fellow students' description over here. But if it is, then it makes sense. Okay, I think unified memory in CUDA just simplifies CUDA malloc. Underlying, it still it needs explicit page migration between CPU and GPU. Okay, this is where we may run into term differences. Maybe that's true, I don't know. This is where Juan can perhaps talk about more. Is Juan online? Maybe not, because he deals with all of this a lot more than I do. Okay, but we may actually have a heterogeneous memory lecture related to this. Okay, so basically, I think the conclusion is I don't think we know the answer to your question about unified memory in Apple. But we can easily figure out what unified memory means in, I guess, NVIDIA's terminology.
Okay, yes, I think that's fun.
But I think I will say something. This GPU and CPU unfortunately evolved in a very ad hoc way. That's why you have this explicit copying that has happened in NVIDIA, and NVIDIA tried to get rid of it as much as possible. I believe they've gotten rid of it somehow. I don't know if it's called unified memory or some other name, but I believe there is a way you can get rid of this explicit copying between CPU and GPU in NVIDIA. I don't know, especially if they're sharing physical memory. If they're not sharing physical memory, I mean, you have to explicitly copy somehow, but I don't know how that works. I don't know what it's called, basically. Okay, but this is a good discussion, I think. Maybe people will be more interested in looking into these systems. Okay, anything else we should discuss? Okay, I'll wait for a minute to see if there are questions or if anyone wants to speak. Feel free to speak if you want to speak. Okay, I guess I don't see any hands, questions, and I don't hear any sound. Okay, so I guess let's finish the lecture right now. I will see you tomorrow when we will talk about emerging memory technology. So hopefully it'll be exciting. We'll talk about especially phase change memory quite a bit, but we will also talk about other emerging memory technologies and what they enable going into the future. Okay, take care until then. Have a good day.